Okay, so in the next section, we want to activate the serial communication. So we want to make a link between our computer and the microcontroller so they can communicate with each other, and basically we can run some codes from the we can run some commands from the uh, PC, and the board can understand. So first thing is that we need to know about the serial communication. So I'm not gonna go deep into the details, just very briefly. You remember that you were using a function, GPIO toggle or GPIO write pin, to turn on an LED or turn it off. So basically, using the same principle, you can, um, let's say in simple terms, you can turn on or turn off a pin. By turn on, we mean that you will connect that pin to 3.3 volt in our case, or when you turn it off, you just connect that pin to the ground, which is 0. By toggling that, for example, as you can see here, you can stream a set of, let's say, bits here, and then if there would be a receiver on the other side, it can basically understand the data that you're trying to send to the receiver. Okay, so that's the basic of the serial communication. So in serial communication, we have, let me find a better picture somewhere. Yeah, I think this is good. So you will send your data in several bits, so 0 1 0 1 0 1, and then the other side there would be a receiver which will receive that. We have also the parallel interface where you are connecting several pins, for example 8 pins here, to the receiver, so from transmitter to the receiver, and then using that you're communicating. So this will be the parallel interface, and then we have the serial interface, which you just toggle a pin to indicate a data, and then the receiver will receive that. Okay, so in our case we want to use USB. USB is a serial communication. So let's see, USB communication protocol. Okay, so we have two pins on USB, D plus, D minus, and then we have ground and VCC. Ground is connected to 0, and VCC is connected to 5 volt. Then we have D plus and D minus, which, exactly as I told you, by alternating between 0 and 1 will carry some information. And D plus is, let's say, is the one who's carrying the information, and then D minus is basically the inverted of the D plus signal, and it has some fundamental reason why we are using a D plus and D minus, which will improve the noise to signal ratio, but I'm not gonna go into the details of that. So as you can see here, D plus and D minus, for example, here you can see as it alternates, it shows that the value is 0, and when it stopped alternating, it means that the value is 1. So it's pretty easy, and it's already implemented in the microcontrollers and the PC, so you don't need to be worried about how it's working. So it was a very quick and very brief introduction, and I tried to keep it as simple as possible. So now let's go to the STM32 cube and configure our microcontroller for communication with the PC. So in the microcontroller case, we have UART So we have UART option, which use specific rules for communicating with any device, not just the PC. But we also have USB. I just found out that in our board, sorry, USB, sorry. I just found out that in our board we don't have the possibility to use the um, UART, so we are going to stick to the USB, which is okay. I mean, in our case, it doesn't really matter. We just want to send some information to the PC and receive some information. Okay, let's go to the STM32 Okay, so in this project, we are going to use a USB peripheral, and USB peripheral require a specific configuration. So we need to make a new project using the default setting of the board. So let's go to the STM32 project, then board selector, and then STM32F407 GDISC1. Next, USB communication. Next, and finish. And this is important that we want all the peripherals with their default mode, because we need to use USB, and we need to use USB, and for USB we need a specific clock. So clock basically is the main thing that control how fast your microcontroller is running the instructions that are saved in the flash. I know it's a bit hard to understand because you need to basically pass the microprocessor course probably to fully understand that, but in simple terms, clock is controlling how fast your microcontroller is running some instructions. Okay, so since we need the clock to be at a specific value for this project, sorry, we need to initialize all the default modes, so it will configure the clock for us. Basically, you can see here that it's using the external clock, and then it will configure the 48 megahertz clock, which is important for our USB. And since we want this value here and we want the configuration, so we just initialize everything to the default mode. Okay, so yeah, in this case, it already configured the pins for us, it already configured the clock configuration, and now let's go to the connectivity part, and then USB OTG FS. Okay, so USB can be host, can be device, or can be dual, so it can be both at the same time. So host is the controller that is controlling the USB communication. So it's like a master that's controlling several slaves, okay, in other terms. So when, for example, when you're connecting your board to the computer and you want to communicate with the computer, usually the computer is the host and your board is a device, okay? But in, like, let's say in mobile phone, your phone can be a host at sometimes, or it can be device at sometimes. For example, when you're connecting your mobile phone using a cable to the PC to transfer your, I don't know, pictures or videos, at that moment your mobile phone is the device and the PC is the host. Okay, but there are some occasions that you connect a pen drive or flash drive to your phone, or you connect a mouse, let's say, to your phone. Then at that point your phone is the host, and you see your phone can be host or device depending on the connection that you're having. So that would be the dual role. But in our case, we just want to connect our board to the computer, so we'll stick to the device only. Okay, so after you selected that, you don't need to change anything, just keep that activate VBus. So VBus basically is a is a functionality that will sense the presence of the cable, and if you have the cable connected, then it will initialize the USB communication core in your microcontroller. So okay, so we had this config, and let's talk about this USB communication controller that I told you. So inside your microcontroller, you have a section uh, that is controlling the communication via these two pins here. So this is the D plus, this is the D minus, and these are connected to a USB controller. Okay, so this USB controller using these pins to communicate with the PC that you have, and this is the physical basically layer that is needed for communication. But we also need some software rules and regulation to be able to communicate with the USB, because USB is a standard protocol. So everything who want to work with that USB need to follow the specific rules and regulation that is already there. So for example, let's go to the middleware. So middleware is where we have these um, libraries and rules and tools that are written and we can use. So for example, your USB can be, I mean, your device can be an audio device class. So in that case, it will follow the audio device rules. Okay, it can be communication device, it can be firmware update device, it can be human interface. For example, human interface is the mouse and keyboard basically. So the amount of commands that they can send to the computer is limited, and it's kind of optimized for that. It can be a mass storage actually. So mass storage is for example the pen drive that you have. So when you have a storage and you want the host, which is the PC in your case, to detect it as a drive, you need to use the mass storage class and rules. Okay, but in our case we just want to make the communication, so we want to send some information and receive some information. So in that case we'll stick to the communication device class. Okay, so here there are some configuration that you can change based on your application. We have, for example, the buffer size, which, for example, if you want to receive some big chunk of data, for example, video or pictures or audio, you need to increase the buffer size here, the receive buffer size. Okay, and you can change the device descriptor, which we will talk later on when we need to use this information. Okay, so that's it for the USB configuration. Let's just save the project and generate the code. Okay, so here we have the mix USB device initialization, and it will prepare everything for you. So I always, when I want to work with the microcontroller, I always start with a very simple stuff to make sure that everything is configured properly. So I just write the toggle pin, and then I write LD3 GPIO port, and then LD3 pin, and then I'll delay 1000, sorry. So I run this code to make sure my configuration and everything is configured correctly. For example, if there would be a soldering issue on your board on the USB side, probably your microcontroller will get stuck here, and you can use the debugging tool to see where it's stuck. But for example, that's one of the cases that I want to make sure now it's working. So if I can see the LED blinking now, it means that the code was okay. So I can see the orange LED blinking, so it means that everything goes okay. Okay. Next step is to write a bit of code for configuring the USB communication. But before that, since you already activated the USB controller on your microcontroller, you should be able to see the communication working. Basically, the USB is working. So you should have received a cable with your board. So one cable is connected now to the board for the programming purposes, but you should have another micro USB cable which you can connect to your board on the other, exactly on opposite side of the programmer connector. So if you connect that, okay, let's open the device manager. Okay, so if you scroll down in the ports section, you should be able to see STM32 virtual COM port, not the ST-Link virtual COM port. We are working with the STM32 virtual COM port. And you should be able to see a number, so it's like COM5 here. If you disconnect the cable that you're using for the USB, not the one for programming, but the USB one, okay? So if you disconnect that, you will see that there would be no ports here. And if you connect it again, you can see the ports. Okay, so that's for checking the COM port and the COM port name. Okay, next thing is to download a software that we can use for communicating with the board. Okay, so let's open Edge. Let's search for Hercules. Hercules terminal. Okay, so this is the Hercules software which you need to download. I download it. Okay, so you open it, and then here you'll go for the serial section here, and then COM5, and then the configuration you want, and you try to, oh sorry, this is another program running. Okay, now you open it, and if you saw this message that serial port COM5 open, it means that everything is okay. Okay, so let's go back to the code here. Let's write line of code CDC transmit FS. So for be able to see this, you need to, yeah, no, I thought you need to include something, but you don't need to. Okay, so let's write here, for example, hello. Then here you write how many character or byte are there in the text that you want to send. So hello is consists of 1, 2, 3, 4, 5 character, visible, let's say, character, and then some escape character which you don't see them. So this is the return. So it actually works like the enter button on your keyboard, and this is the new line escape character. So when you use these two together, it means that go to the next line, go to the beginning of the next line. Okay, so these are also one character. So this is one character, this is the another one. So in total we have 7 characters. Okay, so I write 7 here. Then let's try to see if it works or not, but I think it won't work. We have a warning for now, but it's fine, don't worry about it. Okay, yeah, we can see the serial transmit working. Just let me disconnect everything and connect it again to make sure everything is fine. I connect it again. Open, yeah. We can see the serial ports working correctly. Okay. We need to change something as well. So there, if you go through USB device, USB CDC IF, which is interface, you need to add a couple of line of code. So here we have CDC set line coding and get line coding. Okay, so these are used in some application for getting the configuration of your port. For example, at what frequency it should communicate, what is the parity. Parity is used for detecting basically some of the problems that might happen. Then number of bits that you're sending, you can send 5 bits, you can send 8 bits, or you can send 16 bits. So the best thing that I would suggest you to do is that you basically here set line coding. The PC, the host that you're trying to communicate with, will tell you what user preferred. So user from here, they can choose the configuration that they want to use to connect to your port. And you can get this configuration that user applied, and then you can save it. And if so, then later, for example, a program asks you the configuration, you can just simply pass them the configuration from here. I know it's a bit seems confusing, but you can just for now just follow what I do here. So let's go here and add a private variable. We need 7 characters, and here we implement that 7 characters. And notice that this section is inside a user code begin, so if we change anything here, it will stay there and it won't disappear later. And as you can see, we have like from 0 to 6, which is 7 line coding structures. So we just write a line of code here. So basically you can receive the structure from this variable, which is pbuffer. Okay, so you just need to first here you need to save that. One, two, three, 4, 5, 6. Okay, 6, 5, 4, 3, 2, 1. Okay, so here we receive the pbuff, and we receive the configuration that user applied through the software that they are communicating, and we receive it here. Then later, if somebody or a PC or any host wanted us to send them the configuration, we just use that data to send it to them. Okay, so that's it. That's all you need for this part. Let's run the code again. It's especially useful when you're writing your own programs in Python or Java or any kind of software that you want to use. So that's why we need to write this. But for Hercules, it doesn't really need it. Okay, so again, we are seeing the hello, and next step is to receive something. Okay, so we want to send something, and we would like to receive it on the board. Okay, so let's debug the program. Okay, so there is a function inside USB-D CDC here exactly. CDC receive underline FS. FS stands for full speed, and we have a receive function that basically will be called upon receiving something. So let's put a breakpoint here, and let's try to send something to the board. Okay, let's run. Okay, let's send a text test. Oh, sorry, I should close and open it again. Now let's send the test. Okay, so you can see that breakpoint stopped here, and basically let's see what these functions are doing. USB set Rx buffer, so it should be a function. Let's search for it. It's a function inside. Okay, set Rx buffer. It should be a function somewhere, probably in the drivers. USB, hopefully. Yeah, probably it's here. Let's try to find it again. It's in USB-D's underline CDC.h. So if it's here, it should be in the relevant C file. So it should be in this middleware. Okay, it should be in middleware st device class CDC source. It's weird that it didn't find it for us. Okay, so it's here. Okay, it doesn't do anything particular, so basically it will set the Rx buffer to what we give. So what happened here is that we have a buffer probably somewhere. Yeah, user Rx buffer. Yeah, okay, so basically it set the buffer. I don't want to go into the details, but just very quickly. So you have probably a structure somewhere, probably this one. Yeah, so this structure basically it's like an interface in JavaScript, in Java. So you have some functions that you need to implement. So here you can see it basically implemented those functions and set them for the USB interface. So where it used this, and we also have a USB CDC handle type def. Let's go back here. Okay, so this is the USB that we are working with. But where is that where we set this thing? Okay. So we are basically here we have a user buffer, and then here when we are initializing the USB communication and CDC layer, we basically set this buffer. So here, for example, you can see it set the TX buffer and then set the RX buffer. And then later when we receive something, it set the received data. Yeah, it set the RX buffer probably to a temporary buffer, and then it tried to receive that packet. So it basically probably here will copy some let's see, what did this function do? Prepare out endpoint for reception. Prepare, so this function clear the input endpoint, which is output endpoint basically, because we are talking from the host side, and so and the host will output some data on the endpoint. So we'll clean that. Okay. So let's see what is inside these variables. So this buffer, okay, so the buffer includes the test a string that we send, and let's again check this one. Why there is no description of this? And then okay, so yeah, in this set RX buffer, basically we are first in the init, if you remember, we set the RX buffer address. Okay, so we set this buffer address, and then here we just connect that received data, which is in the buffer, and it was here basically in this buffer. So we are setting the address of the RX buffer to the buffer that we have from USB. So basically we are connecting what we received to the buffer. Okay, so it's clear now. So we have the data in the where was that? Yeah, our user RX buffer fs. Okay, so let's go forward. Okay, we're here. Let's run this code again. Let's put the breakpoint here, and then let's try to send another thing just to verify what we said. So we should have, okay, so we should have the data in this user RX buffer. Okay, so just let's add this here to make it easier to work with. Yeah, so yeah, we have test one, sorry, until here. So we have test one received here. Okay, so let's write the function here to call, we will say handler, to handle this data that we received. Sorry, not in the init, in the receive. Okay, so let's write a function here, USB rx handler, and then let's pass the user rx buffer fs to this function. Okay, so this function we implemented in the main here. Okay, wait, 80. So we want the address of the buffer. Okay, so this will be called upon receiving something. So here should have something that we received. We can just basically, for now, we can keep it there, return. Okay, we'll put a breakpoint here. Let's go here, and what we need to do is that we need to define this in the main.h, include main.h, then user code private external function. Yeah. Okay. So now probably we should be able to call that function. Let's build. Run test2. Oh, I forgot to close this and open it again. Okay, test2. Oh yeah, we received it. So we have the buffer here, which is test2, and that's what we need. Okay. But there is a thing that I'm a bit worried about. So how do we define the length of the received data? I mean, you see it's here, let's say buffer. So we have test2, and then we have some other stuff here. But for now, we just want to have the test2. So we should find a way to detect this and to know that the rest is not okay. The rest is not relevant to our data. So whether we find the length of the received data, or if we didn't find that, we should put a special character, like a new line character here, so we can find out that this is the end of the text that we sent. So let's go back to the USB here. Let's see if we have the length of the received data somewhere. Or maybe it's better if we stop it here, because there might something happen here, so it cleared the information about the received data. So let's try it again. Let's send test3 this time. Okay, so buffer has the test3 plus some irrelevant information, and then let's see where we can find a state. Sorry, the length of the data that we received. So CDC data out, it called from here. So here we have the length exactly, but receive length. So we should have receive function somewhere. Yeah, okay, yeah, it's here. It's here because basically it called this buffer, and then it has the length here. So what we do is that we just pass this length here, then we go to the main, and then we make a new variable here, copy this, new parameter, sorry, and then paste it in the main.h here, and then let's try. What happened? So len undeclared first using this function. Oh, sorry, it was len and it's the address of the lens. So probably we need to change something here. Let's try. Okay, it's working, but let's see. Run, and then Hercules, close, open, test 4, send. Okay, so we have lens here. What happened when we pass it to the function? F5, so F5 goes into the function. Do we have lens here? No, because that's a pointer to the lens. So in order to get the lens, what we can do is that maybe probably adding this pointer here will give us that value. Let's try it. Okay, yeah, it worked, and we have the lens. Okay, so now we have everything we want. So let's write a function. If strcmpn, which is a function, I think, if I'm not wrong. Let's include the library first. So it's a function from string library. Let's write str. What was it? strncmp. Yeah, strncmp. Sorry. Okay, so it compared two strings together. So let's write if we received buffer and it was equal to high for the lens that we received, or basically let me think here, because there would be an issue if we send, for example, test 1. No, it should be okay. It should be okay. So let's write high here, and then if it was 0, so basically if it was identical, if you just have a look for strcmp function, strncmp, see the string to be compared. So the first and second parameter are the string, and then num or number is the maximum number of characters to compare. And if it return 0, it means, sorry, I should turn this off probably. Okay. If it returns 0, it means that the content of both strings are equal. Okay, so let's write this, and if the buffer that we received was equal to high, we should send back. So let's send back CDC transmit fs welcome, let's say, /r/n, and then length is 2479. Let's see if it works, but this is probably not the best way to do this. I'll tell you later why, but it should work. Okay, let's try. So we are receiving that, then we send hi, and we receive welcome. Okay, but if you send something else, you should not receive anything. Yeah, that's true. The hello just printed because it's just a thing that we print all the time. So, but if you send hi, you should receive welcome. Okay, so this was the part for USB CDC. Just one thing before finishing the tutorial is that let's stop the program here and let's see what is wrong. Okay. Let's run the code. Let's send something. Let's skip these parts. Okay, so here you can see your code is stopped here. This is called forgot it. This is called the stack tree. Yeah, it's called stack tree. Okay, so in stack tree you can see the sequence of function calls. Okay, so we know, for example, we are in the USB RX handler. It called from CDC receive FS, so we can see it's called from here, and then the CDC receive FS called from USB D CDC data out. So we can see the sequence of function calls. Okay, if we go back here, we can see OTG underline FS IRQ handler. So IRQ handler basically is an interrupt that that triggered when there is something coming to the processor and we need to process that. Okay, but the thing is that as a general rule, you should not stop the microcontroller in the interrupt handler, because interrupt happen in a way that, for example, just imagine that microcontroller was running something and then this interrupt happened. So microcontroller stopped running that part of the code that it was running and jumped to the interrupt handler to handle that interrupt that happened. Okay, so in the documents and in the datasheet of the STM32, it clearly said that you should not stop the interrupt from running. If you do that, you will encounter a situation called a hard fault handler. So in hard fault handler, basically the microcontroller will stop and you need to restart the microcontroller because the interrupt shouldn't be stopped from running. But what you have here is a function. For now, this function, since it's a really small function, it's fine. If you want to write a couple of lines even more than this, even tens or like even up to 100 lines here. But the thing is that as you add more lines of code here, it will take more time, and probably at some point it will hit that limit that you have to handle an interrupt, and it will cause a lot of problems, and it will cause basically hard fault handler, or it cause the USB to stop responding, and it can like stop your application from running. Okay, so the best approach here is to basically here is to just set a flag. So let's define a flag here. So flag is a simple variable basically that you use to keep the state of the system. Okay, so we will add a variable here, USB data ready, USB RX data ready. Let's say it's better. And let's assign it 0. And here you just need to set that USB data ready 1. Then let's just keep also the length of the USB RX data ready data length, sorry. And let's have also the address of the buffer. USB RX data buffer. Okay, so what you do here is that you quickly will set the flag so you know that you have the data ready. Then you just simply assign the variables USB RX data buffer to buff, and then USB RX data. So you take the information, the important information here, and then that's it. You return, or you basically don't need to return. You just finish the function. So this will help the microcontroller to end the process of handling the interrupt, and it allows it to move forward from the interrupt. But then later in your code, let's say here, I just remove the hello for now. Okay, so you check if USB RX data ready was 1, so it means that you have a new data ready to process. Okay, if you had that, then you'll add this line of code, and for here you use USB RX data buffer, then here USB RX data ready, oh sorry, data length. Okay, so let's try this. So basically here you set a flag to indicate that you have something to process, and then here in your main loop, if you had something to process, you process that. And by the way, you need to clear that flag. Okay, let's try this. So you can see sometimes I stop and sometimes I pause the video. It's because I'm just writing these codes right away. I didn't have any preparation for that, because I think it is more natural to just go with the flow. If we hit any problem, we just fix that problem. So it's a natural thing to see everything from my perspective when I'm writing the code. So probably it will help you. That's how I usually record the tutorial. So I just go with the flow. Uh, if I encounter any problem, I will show you. So there is basically there is no shame if I run into a problem. It just show how we proceed if we encounter any problem. Okay, so let's run the code. Let's see here. Okay, we don't receive the hello because if you remember, we removed the code. So if I send a hi, it should send me welcome with a bit of delay, but yeah, that should happen. Oh, we forgot to, let's see. Yeah, I send the hi, it sent me a welcome. So what happened here is that you set the data ready, you set the buffer address, you set the length of the data, and then here if you had data ready, you just process it and you will do the relevant action. Okay, I think that's it for this session, and that's basically what you need for the USB communication, and I'll see you in the next tutorial.